assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
Okay, problem 42 has the ability to be very complicated, so we're going to take it in a methodical manner. It's essentially a geometry problem, so we have two wires that are parallel to each other, some distance apart, and we want to know the magnetic field at a certain point that is away from the center, so we no longer have a nice symmetry. The magnetic field from each wire by itself is actually quite simple. So the way we're going to approach this is first write, we'll say this is 1, this is 2. We'll write the magnetic field of a wire, 2 pi. And what I've done here is I've labeled each of these segments as A for the shortest, B for the middle distance, and then C for the distance between the wires, so the longest distance. And hopefully that will help us keep things straight. So that's A, because it corresponds to this distance. And the magnitude of this field is 9.333, that ought to be enough, times 10 to the minus 5 Tesla. And then B1, how about B2 instead, is exactly the same, except now, instead of A, we have the distance B. And we're going to be skipping a lot of the calculations and such, just because it's not something that is vital, I think, to the problem. So these are the magnitudes of the fields at the point. Now what we need to do is figure out the angle that the radial line is going to be to. So the thing about when you have a wire, if we have one over here, and this has a current coming out of the page, there's a magnetic field that goes around it like this in that direction at every point. It's always normal to the line of the circle. So we need to take our vectors from both of these and add them up. So we'll have some angle here. We'll call that angle 1. Call this one angle 2. So we have theta 1 and theta 2. And we need to figure what those are so that we can sum up our vectors. Now, like I said, this is a bit of a geometry problem, and sorry that this whole thing's looking a little messy. And what we're going to do is use the law of cosines to determine the angle that the radial lines make with the vertical line, because that's the line that the magnetic field is going to make with the horizontal line. So law of cosines here, if we want to do theta 1 first, that's going to be inverse cosine a squared plus c squared minus b squared divided by 2, that is an ugly 2, 2ac, and that is 47.7 degrees. And then very similarly, we do it for theta 2, which is b squared plus c squared minus a squared over 2bc. And that is 26.3 degrees. And you should always check these to make sure that the answers you're getting make sense geometrically. And in this case, I say they do. My picture's already messy, so I'm not going to draw anything here. But draw out the vectors and see if they are what you'd expect with the horizontal line. And We can now skip to a new page and write the, since we have the magnitudes and angles, we can calculate the total net magnetic field. So first we'll do in the x direction, so we'll say net x, and that is going to be the cosine components. So B1 in this case is defined positively, so it has a positive sign. Subtract the magnitude of B2 times cosine theta 2, and crunch those numbers, and you get 1.261 times 10 to the minus 5 Tesla. And you do something similar for B net Y, except they're both defined positively here. So B1 sine theta 1 plus B2 sine theta 2. And you crunch these numbers and you get 9.384 times 10 to the minus 5 Tesla. And finally, we need the magnitude. Like I said, this is a long problem. And the magnitude of a vector is bx squared plus by squared. If we're only in 2 dimensions, there'd be a z if we were in 3. And that magnitude is 9.468 times 10 to the minus 5 Tesla. And finally, we want, so this is our total magnitude. Let's not forget this. And then the angle that this total vector makes is simply inverse tangent by over bx. And you get 82.3 degrees. Thus, if you write it out in this explicit way, you get that your total B vector for the magnetic field from these 2 wires at that point is 9.5 times 10 to the minus 5 Tesla at 82 degrees. So we skipped over some of the tedium, but I think I didn't skip anything that was ground shaking. And we'll box it for posterity.